clearly transistors are on this layer here, devices, and we're working our way towards digital circuits. In the next video, actually, we'll finally make it to our desired destination, which is digital circuits. But we're actually going to bounce around quite a bit today. We're going to talk a little bit about this lower level of abstraction down here. Electrons again, even though we had already passed that in the first video, it is going to be worth talking about some of the physical layer stuff again, and we'll also maybe touch on some analog types of things throughout this video as well. So we're kind of in the bottom three layers for this particular video, and starting with the next video we're going to be in this layer of abstraction, and we're not really going to worry about these lower three layers very much anymore after we get through this particular video. Okay, so let's talk about transistors. There are actually two types of transistors that are worth talking about. And so here you can see the schematic symbols for both types. We've got NMOS transistors and we've got PMOS transistors. You see that they have the same pieces. So there's a gate, there's a drain, and a source on each of these transistors. And you'll remember from our last video, we talked about transistors as switches controlled by electricity. And so the gate in this particular case is the actual switch itself. The electricity is going to be applied to the gate that will turn the transistor either on or off. And so then when the transistor is on, current will be allowed to flow between the drain and the source. And it actually can flow in either direction. The direction that the current is flowing is not particularly important for our purposes, but you should know that it's going between the drain and the source. Now, the difference between NMOS and PMOS, you'll notice on the schematic diagram, the only difference between the two is this little circle here on the gate. And that's an important distinction. So what that means is, for an NMOS transistor, I have to apply a positive voltage to this gate. So I have to apply a 1 in the binary system to turn this gate on to allow current to flow through the system. If I don't apply voltage, if I apply a binary 0, in other words, then this transistor will be off and no current will be flowing from drain to source. The PMOS is the exact opposite. So in a PMOS transistor, if I apply voltage to the gate, if I apply a 1, a binary 1 to the gate, the transistor will be off and nothing will flow through. If I apply 0 voltage, or if I put it to ground, to use the electrical term, ground is equivalent to 0 voltage, then the transistor will actually be on and current will be allowed to flow through this particular transistor. So the switch will be active. It will be activated. So these are kind of complementary transistors, which is very important, as we'll see when we start to talk about the components of digital logic circuits in the next video. So how do these transistors actually work? I want to actually talk a little bit about the physics behind these transistors because I think it's particularly important. You've probably heard the word semiconductor thrown around when talking about computer chips, when talking about transistors. In this case, the semiconductor is going to be silicon. So over here on the very left, you can see we've got some silicon that is the primary component of all transistors. And by itself, silicon is not a very good conductor of electricity. To think of a real-world example of silicon, it's in a lot of rocks or sand, right? It's not exactly the same thing, but there's a lot of silicon in those substances. So it doesn't conduct electricity very well by itself. However, the reason it's so useful, the reason that we use silicon in our transistors, is because it does attach to other elements particularly well. So in this case, if you look at the middle diagram here, we've done what's called doping on this silicon. So we've added an atom of arsenic to this grid of silicon, which bonds very well with the surrounding silicon. The arsenic does. And so by adding this arsenic into the silicon system, we've managed to come up with an additional source of an additional positive source in the system, which is going to attract an additional electron into this silicon arsenic system. So we have an extra electron now floating around. An electron, of course, has a negative charge. So this system is what we call negatively doped. It has additional electrons available. than it would otherwise normally have if it were pure silicon. And then on the far right, you see we've got boron here in the middle, which is kind of the opposite, right? Boron has boron is going to boron is going to attract an additional electron, which means that the silicon will be missing an electron, right? So it wants an electron to be here, but there isn't one left because the boron has taken it. And so this is what's called a hole. There's an empty space where an electron should be, right? So this hole, this absence of an electron, can be thought of as a positive charge, which means that this is positively doped. Or in other words, we say that the arsenic doped silicon is going to be N-type, and if we use boron with the silicon, it's going to be a P-type semiconductor. So all transistors are composed of N-type and P-type semiconductors. And if you'll notice, if you'll recall back, we had two different types of transistors that were NMOS and PMOS. That's very directly related, as we're about to see. So we have these two types of semiconductor materials. When we combine the two together, we get what's called a diode. So here you see I've got some P-type semiconductor material with the boron and some N-type semiconductor with the arsenic placed side by side. This forms what's called a diode. You see the two parts here. Here's the schematic diagram for a schematic symbol for a diode down here at the bottom. The way a diode works, if the voltage of the P-type side is higher than the voltage on the N-type side, then current will flow through from left to right. It only goes in one direction, right? It can't go backwards from the N-type to the P-type. It can only go from the P-type to the N-type. And it will only flow if the P-type voltage is higher than the voltage in the N-type, right? If the P-type voltage is lower than the N-type voltage, then the diode is effectively off. Current cannot flow through at all. There is no current flowing through this particular diode. And so a transistor then is sort of comprised of these diodes. Let's take a look at what a transistor actually looks like. So on the left here you can see an NMOS transistor with the N and P semiconductor areas labeled. And then on the right side you can see this PMOS transistor with the P and N semiconductor areas labeled. And there you can also see the reason why they're called NMOS and PMOS. The reason it's called NMOS is because the source and drain are N-type semiconductors. These are called wells. The source and the drain are called wells that are embedded in a base layer of P-type semiconductor material. And then the PMOS is the opposite. The PMOS has two P-type wells, right, with an N-type semiconductor substrate layer forming the base. The other parts of the transistor that you can see, this polysilicon, or it actually used to be just metal that used to sit on top of the gate. And then underneath that, some silicon oxide, which you can think of as just glass. So remember, the gate is what controls the switch. The gate is what determines whether the transistor is actually on or off, as we're about to see here very shortly. And so there's kind of an insulation effect between the voltage that is or isn't applied to the gate and the actual substrate itself. So now that we know the pieces of the transistor, how do they actually work? Well, let's take a look at the operation of the NMOS transistor. Remember, the NMOS, the switch is on if there's a voltage applied at the gate, and it's off if ground is applied at the gate. So here on the left side, we see the gate is connected to ground. Ground is represented by this little empty triangle here. Right? So the gate is connected to ground. And recall from our discussion that there's actually diodes here. So these N wells in this P substrate form two diodes that you can see in this particular diagram, right? So in order for these diodes to be operational, the voltage of the P-type has to be higher than the voltage of the N-type. And in this particular case, the P-type voltage is 0. There's no voltage applied to it at all. It's applied directly to ground. And so the N-type is going to be 0 at best, right, or higher potentially, which means that nothing is going to be flowing through this transistor. It's essentially blocked off. If we want to turn this transistor on, if we want to flip the switch, we need to apply a voltage to the gate. So that's what we see here. VDD is a voltage that's being applied to this gate. And so here you see this positive voltage applied to the gate, which is going to attract electrons on the other side of the silicon dioxide, on the other side of this piece of glass. It's going to attract these electrons to these positive charges over here, to this positive voltage, and it forms a channel. So this channel is now effectively N-type semiconductor. We've effectively switched the type of this to N-type from P-type. And it creates a little channel that bridges the two N wells together and allows current to flow through between the source and the drain. In order for this to work, this voltage has to be above a certain level. That's called the threshold voltage. Typically this voltage is between 0.3 and 0.7 volts. So if I apply less than 0.7 volts, it's effectively grounded. It's effectively 0. If I apply more than 0.7 volts, that's effectively a binary 1. The transistor will be on, and it will be conducting current through this particular transistor. So just to kind of reiterate, right, we saw the physical specifications of how transistors work. We're not going to spend a whole lot more time talking about, the electrons moving through the transistors, but this is the main takeaway from this particular video. Right, we have two different kinds of transistors, NMOS and PMOS, and they work sort of complementary to each other as switches. For NMOS, the switch is on if voltage is applied to the gate, and off if it's not. For PMOS, the switch is on if voltage is not applied to the gate, and off if voltage is applied to the gate. This is going to allow us to construct the basic building block of digital circuits, which are logic gates. That is the topic for our next video. So with this video, we'll finally arrive at our destination, at least for the first part of the course, which is going to be, this digital circuits layer of abstraction that you see on the hierarchy here. So after this point, we are going to talk a little bit more about transistors, of course. We're going to build on the last video. But after this point, we're not going to spend a whole lot of time, in fact, we're not really going to spend any time on these bottom three layers of abstraction here. The whole point of getting to this digital circuit layer is so that we no longer have to worry about these bottom three layers anymore. We've removed these layers of complexity from the equation, and now we are that allows us to focus on the things that we care about in this course, which are digital circuits, logic, computer architectures, etc. So from here on out, we're going to be living in these layers of abstraction up here, right? That's going to be the topic of the rest of the course. So in our last video, we saw transistors, and we saw how they work from a physical perspective, right? Electrons, current flowing through, basically treating the transistors as switches. Now we want to apply this to digital logic, which I'm sure you were all introduced to digital logic in the introductory class, so you saw things like ands and ors and nots, right? And with those particular logic functions, we can do things like add numbers together. We can do things like store information. We can do things like determine what operation should be performed next on a particular computer. So those logic functions, while very, very simple, can be built up to do some very, very complex operations on a computer. So they're a very, very important part of not just this class, but of computing in general. So let's take a look at how we can use transistors to start to piece together these logic gates that are the building blocks of our computer. Here's an example of two transistors, right, put together. You can see at the top we have a PMOS transistor. I know it's a PMOS again because there's a little circle here on the gate. And down here at the bottom you see I've got an NMOS transistor. I know it's an NMOS because that little circle is not there. In addition, at the top here we have a positive voltage, right? And at the bottom we have ground. So there's a path actually from this positive voltage to ground through the sources and drains of these transistors. Notice that the gates are not connected to the sources and drains at all. It's not really necessary, at least not for this particular example, for the gates to be connected to the rest of the circuit. There's sort of a division there between the gates and the sources and the drains. So on the left side here, the label marked A, that's going to be our input. And on the right side at the value marked Y, that's going to be our output of this particular circuit. Again, we're dealing with binary, so our input basically consists of two values, 0, which is a 0 voltage, or 1, which is some positive voltage, right? So if we look at the case where our input is 0, where there is a 0 voltage applied to our input, notice what happens. That 0 voltage is attached to the gates of each of these transistors. When 0 voltage is applied to an NMOS transistor, the NMOS transistor is essentially off. The switch is in the off position, which means that no current can flow through this transistor. This bottom half is effectively off. It's not in use. When 0 voltage is applied to the gate of a PMOS transistor, it's on. So current can flow from the source to the drain. And so you'll see that that's what's happening in this particular case. This positive voltage, this binary 1 voltage, is flowing through the PMOS transistor to the output. It's not going to ground, remember, because this transistor is off. It's effectively off. So that's what happens when the input is 0, the output is 1. Now if we look at the other case, when the output is 1, the opposite happens. The PMOS now is going to be off. The PMOS transistor will be off when a positive voltage is applied, so nothing can flow through it. The switch is in the off position. But the NMOS will activate. The NMOS will be switched on, which allows current to flow. And what that means then is that the output is directly connected to ground, directly connected to a 0 voltage, which means that the output of our circuit is going to be 0. So what we have here is a circuit that takes our input and flips it. If I put a 0 in to my input, the PMOS will be on and the output will be 1. If I put a 1 in to my input, the NMOS will be on and the output will be 0. So whatever I put in, I get the opposite of that as my output. This is how a NOT gate is constructed. If you remember from computer science, a NOT just takes a Boolean value, right? A true or false value, a 1 or a 0 value, and it flips it. It makes it the opposite. So here we're taking in false and we get true back out, or we're taking in true and we get false back out. This is how we construct a NOT gate, a NOT logic gate. This is constructed of two distinct pieces. You'll see when you're looking at how gates are constructed, like in the textbook, for example, there's an additional example of how gates are constructed. You'll always see PMOS transistors at the top, and you'll always see NMOS transistors at the bottom. So this section of PMOS transistors, that's called the pull-up network. Reason being that when those transistors are on, it's going to pull the output up to a positive voltage, to a positive, to a binary 1. And then the NMOS transistors down here at the bottom, the collection of NMOS transistors, is called the pull-down network, because when those transistors are on, it's going to pull the output down towards ground. They will never be on at the same time, at least not within a single logic gate. So either the pull-up network is activated, pulling it up to 1, or the pull-down network is activated, pulling it down to a binary 0. Right? And every logic gate that we talk about in this class is going to consist of those two parts: a pull-up network comprised of PMOS transistors and a pull-down network comprised of NMOS transistors. Right? So the other logic gates that are worth talking about, you see on this particular slide. You've also seen these logic gates before in 131 when you learned Java, right? But the difference here, I want to reiterate, is that these are actually in hardware that we're talking about now. Java is software. Java is code, right? These are actually in hardware. These are actually physical gates that exist. So here we see an AND gate, an OR gate. You may not have seen an exclusive OR gate, right? That's what this third one is. And then the inverter, or the NOT gate, right? So AND, OR, and inverter, I expect you to have seen those before. I'm not going to spend a lot of time going over those. I will briefly go over exclusive ORs, because I'm not entirely sure that you've seen it. So an OR gate, right? If X is high or Y is high, is a binary 1, then the output will be 1, right? If they're both high, then the output is also 1. The difference between OR and exclusive OR is that if both X and Y are true, are binary 1, if both inputs are true, then the output for an exclusive OR will be false. So for exclusive OR, it has to be exactly one input that is true. It can't be both. It has to be exactly one that's true. Exclusive OR is very, very important for other things that we're going to see as we go through the course, so that's why it's good to introduce it now. There's a couple of other really important concepts on this slide that are worth talking about right now as well. You'll notice that on the right side of each of these logic gates, we see the output represented as an expression. So x and y are my inputs to the AND gate. X times y is the output to my AND gate. So we're going to use multiplication in this course to represent an AND operation. For an OR operation, we're going to use addition. So x and y are my inputs. X plus y is the output of an OR gate. We're going to use plus to represent OR. And you can see exclusive OR is represented as a series of addition and multiplication. And for inversion, you see prime listed here. So x prime is going to be the opposite of x. Right? So if x is true, x prime is false. So those three symbols start to form Boolean algebra, which is going to be the topic of pretty much all of next week. These are the first Boolean algebra expressions that we've actually seen in this course. There's going to be a lot more to come. Another important thing that you see here on this slide are timing diagrams. So here we see signals that change over time. Up at the top we see signals for x and y. When the signal is low, that represents a binary 0, right? And when it's high, it represents a binary 1. So here you can see the inputs are 0, 0, 0, 1, 1, 0, 1, 1. So all four possible inputs are represented by these top two rows in the timing diagram. And then the remaining values down here you can see are the results of the AND, OR, exclusive OR, and inverter gates. So you can see that, for example, when x is low and y is high, that's 0 or 1, which is going to return a 1, right? When x is high and y is high, you see that x or y is 1, but x exclusive or y is 0. That's the difference. You can see here clearly the difference between the two types of OR gates, right? We're going to spend a lot more time talking about timing diagrams in the next few weeks as well, but I think it's important to introduce these concepts now. Another useful concept that you've probably already seen, but also worth talking about, are truth tables. So here you can see the same information that was actually presented on the previous slide, but perhaps in a easier to read format. So here we see the inputs listed, and then the output in this particular column. So 0 and 0 is 0, false and false is false, right? True and true is true. True or false is true, right? And so we'll be seeing truth tables coming up a lot in the coming weeks as well. So that's our introduction to logic gates. These are the basic building blocks of all digital circuits. It's very, very important for you to get used to how these logic gates work. And we're going to do some practice in class to make sure that everybody's on the same page regarding these gates.